Grassmannian. Another case is quantum cohomology. So-called small quantum cohomology.
You're saying that these people have characterized this factorial Schubert phenomenon?
It's a factorial. Already characterized
By these people?
by Knudsen and maybe Morev and Sagan. Morev and they are combinatorialists. Morev and Sagan. Morev and Sagan originally studied factorial sugar polynomials. Before Knudsen described the Grassmannian, cohomology of Grassmannian.
What's the first name of Tao?
Tao はT Tao TモレブさThe situation is analogous for the quantum cohomology. Additively, quantum cohomology of the Grassmannian is given by in this case generated by quantum Schubert classes. And Q is a formal variable. The variable Q has complex dimension m. However, so additively quantum coverage is completely discovered. However, the multiplication usually denoted by star to distinguish the ordinary cup product is given by quantum multiplication. Quantum multiplication is quantum multiplication, quantum product. Quantum multiplication is related to the Gromov-Witten invariant. The reference is maybe Aaron Bartram. Bartram is the first who studies the quantum cohomology of the Grassmannian. Bartram, quantum Schubert calculus. For those who are interested in quantum cohomology, please consult this paper. So anyway, additively, the cohomology and the equivalent quantum homology is completely described. So the problem is to describe the multiplicative structure, determines the cup product structure. So next section.
The right hand side is it's just a group structure, right? Is there a ring?
Ring structure.
So you have ring structure. Can't you get ring structure from there? I mean, you have. If you know this image of Schubert, then can't you get from this ring structure? You know that this is injected. So don't you understand the ring structure of the covariant cohomology?
We can identify ring homology.
This is ring injected, yeah.
So we can identify the T equivalent cohomology subring of this thing. And GKM condition by the GKM condition, the GKM condition asserts that the family of polynomials, whether the family of polynomials are in the image of IT star. This is GKM condition. So given family of polynomials,
whether this one is the image or
if image IT star, if and only if I don't know the precise, if lambda minus with なんかイデアルジェネレイティとアルファラフトとアルファラムダサーチコンディションちょっとGKMコンディションin the paper of Knudsen and Tao, they define the T equivalent cohomology as the image of IT star. They define the T equivalent cohomology.
so their ring structure then is understood, right?
Ring structure.
No, it is not. Because you know that it has the image is a subring. So what do you want to know? You know that if this is a polynomial.
Yes.
Also described by the Schubert variety.
Yes. So yes.
But usually description from this description,
It's
we do
difficult
not.
to get. So how do you get this one in terms of this
Yes.
summation of
C2T. So in the context of Schubert calculus, the main problem is
how to get this
yes,
coefficient?
so-called structure constants.
That's one of the main
Topic.
of Schubert calculus.
Yes. So anyway, so we must describe the ring structure, multiplicative structure of the cohomology. Cohomology of the Grassmannian. Part 1.
If you know the ring structure, then how about algebra structure? This one. Is it something? Yeah. Algebra structure as a H star T T H star T point. The algebra, understanding algebra structure is
Maybe coming from the ordinary Schubert calculus.
so you have to multiply this element with something in the ring. I mean this BT. Let's see what that is. And never mind.
Of course, ring presentation is known. No, ring presentation, no. Yes, ring presentation is known. But however, it is not. It is not useful to describe. Yes.
So you want to know exactly what
Yes.
it is.
So the standard problems in the Schubert calculus is the following. First, the so-called structure constant problem. Structure constant problem. Namely, by the basis theorem, the product of two Schubert classes is a linear combination of other Schubert classes. Where and the integers C lambda mu nu is called structure constant. And one of the main problem of Schubert calculus is give a formula for the coefficients. C lambda mu. It is desirable to give a combinatorial formula for the coefficients C lambda mu. And second problem is Jamberi. Jamberi is Italian geometer. Jamberi problem. Jamberi problem is stated as follows. Find generators, ring generators. Find the generators of the ring of the Grassmannian. And express an arbitrary Schubert class sigma lambda in terms of these generators. This is a Jamberi problem. And in the case of complex glass mania. These two problems are completely solved, which I will explain later. In this section, I will describe the multiplicative structure. So let me begin with let me describe easiest case. First we describe Poincare duality. Using the Schubert classes, Poincare duality is easily described. Partition. Let lambda be a partition contained in the rectangle, and Rn. Let lambda check the dual partition. Suppose lambda plus mu equal to Rn, then the Poincare duality is given by the following formula. Product of two Schubert classes. The weights are sum of the weights are equal to Rn. Is when if u equal to the dual partition, otherwise 0. Therefore, the intersection number which we denote integral sigma lambda equal to 1 if mu equal 0 otherwise.
So in other words, you have a complementary dimension.
Complementary dimension.
Then
Yes.
multiplication structure is known.
Yes. In this case, the product structure is no. So using the Poincare duality, the structure constant C lambda mu nu is given by 3 point sigma lambda sigma mu sigma nu dual. So from this expression, it follows that this expression. So geometrically, this is the number of triple intersection. New dual. Triple intersection. So in the language topology, the structure constant is given by the cup product of cohomology. In the algebraic geometry, they are given by triple intersection numbers. So many algebraic geometers consider this triple intersection. Very interesting, but very difficult. The general flux.
So how long ago was it now?
About 1970.
So shortly after Borel result.
Yes, sure this. Kramer, disciple of Zariski, he studied this triple intersection Schubert calculus.
Quite independently of Borel.
Yes. General flux. And the second, next we must mention about the multiplicative structure of the class 1 is PL formula. When you study the Schubert calculus, please remember the name Pieri and Giambelli, Italian geometer. Pieri Giambelli is often.
It does not matter which, this Schubert varieties, does not matter which lab you are choosing.
It's Schubert class is yes. So we change reference flux so as to two Schubert varieties intersect transversely. So the point is the choice of reference flux. It's difficult to choose reference flux so as to two Schubert varieties intersect transversely. It is very difficult geometric problem. However, in the language of cohomology, it's independent of flux.
Also, the triple intersection, as in definition, you have to choose transversal flux.
Yes.
By appropriate choice of transversal
Yes,
flux,
yes.
It is defined.
So, for example, standard flux is we define E1 spanned by E1 to EY. The opposite flux usually the omega tilde is omega 0 tilde omega 1 tilde equal EM omega F2 tilde EM minus 1 and then, so in this case omega lambda F dot transversal omega あれ F dot っていうのだった These two Schubert variety intersectだったかなちょっとラムダコンプリメントだったオメガ 目が、ラムダデュアルパーティションがコンプリメンタリー、かな。transverse intersect transversely. So this translates into
So it will be
Sigma.
finite remaining numbers.
is
The section will be
1 point.
just 1 point.
Just 1 point. Just one. It is easy to check that this intersection is 1 point. So that language of cohomology sigma lambda check 1 in is
So if you choose this opposite.
opposite. Yes. So it's time to okay, I'll finish. Yes, it's
Start here.
yes.